Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our sun, the temperature at the centre reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain. Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected, the antimatter counterpart of an electron. A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light, and energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has two protons and one neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, two helium-3 nuclei collide and fuse, forming ordinary helium-4, which has two protons and two neutrons, and releasing two protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into one helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction, and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity, Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our Sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the Sun is actually a fairly average, middle-sized star. Some massive stars output 1 million times more energy than the Sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the Sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the Sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars. How we find planets around other stars. For most of human history, planets were only known to exist in our own solar system. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye, and with telescopes came the discoveries of Uranus and Neptune. But beyond our solar system, despite billions upon billions of stars filling the galaxy, no one had ever confirmed the existence of even a single planet orbiting another star. The problem wasn't that exoplanets, planets around other stars, didn't exist. The problem was that they're extraordinarily difficult to detect. A planet is tiny compared to its star, produces no light of its own, and sits right next to a brilliant star that outshines it completely. Trying to see a planet next to its star is like trying to spot a firefly hovering next to a searchlight from hundreds of miles away. The first confirmed exoplanet around a Sun-like star was discovered in 1995 by Michel Mayor and Didier Queloz, who shared the Nobel Prize in Physics in 2019 for this groundbreaking work. They didn't actually see the planet. Instead, they detected its presence indirectly by observing how it affected its parent star. This indirect approach has proven to be the key to finding exoplanets, and astronomers have developed several clever techniques that reveal planets without ever actually imaging them directly. The method Mayor and Queloz used is called the radial velocity technique, sometimes known as the Doppler wobble method. The basic principle relies on the fact that a planet doesn't simply orbit its star. Rather, both the planet and the star orbit their common center of mass. Imagine two ice skaters holding hands and spinning around. If one skater is much heavier than the other, the heavy skater barely moves, while the light skater whips around in a large circle. But the heavy skater does move slightly, wobbling around their common center as they spin. The same happens with stars and planets. Jupiter, the most massive planet in our solar system, causes the Sun to wobble slightly as both orbit their common center of mass. The Sun's wobble is small. It shifts back and forth by only about 13 meters per second, roughly the speed of a bicycle. But this wobble is detectable. As the star moves toward Earth, its light gets slightly blue shifted, compressed to shorter wavelengths. As it moves away, the light gets red shifted, stretched to longer wavelengths. By measuring these tiny shifts in the star's spectrum with extremely precise instruments, astronomers can detect the wobble and infer that a planet must be causing it. The planet Mare and Queloz discovered, orbiting a star called 51 Pegasi, created a much larger wobble than Jupiter creates in our Sun, because this planet is both massive and very close to its star. It completes an orbit in just over 4 days, compared to Jupiter's 12-year orbit. The close proximity and short period make the wobble more pronounced and easier to detect. This planet, later named Dimidium, shocked astronomers because it's a gas giant similar to Jupiter, but orbiting closer to its star than Mercury orbits our Sun. Before this discovery, most astronomers assumed that giant planets could only form far from their stars, where temperatures were cold enough for ice to exist. The discovery of hot Jupiters revolutionized our understanding of how planetary systems form and evolve. The radial velocity method works best for finding massive planets close to their stars because these create the largest wobbles. Small planets like Earth create wobbles so tiny that they're difficult to detect even with the best current instruments. A planet similar to Earth orbiting a Sun-like star at Earth's distance would cause a wobble of less than 1 meter per second, slower than walking pace. Detecting such minute velocity changes requires incredibly stable spectrographs and careful corrections for other sources of stellar variability, like star spots and convection in the star's atmosphere. The second major technique for finding exoplanets is the transit method, which has discovered more exoplanets than any other technique. A transit occurs when a planet passes directly in front of its star, as seen from Earth, blocking a tiny fraction of the star's light. For a Jupiter-sized planet transiting a Sun-like star, the star's brightness drops by about 1%. A small change, but definitely measurable with precise photometry. For an Earth-sized planet, the drop is much smaller, only about 0.01%, but still detectable with sufficiently sensitive instruments. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to detect transits. Kepler monitored the brightness of more than 150,000 stars continuously for over 4 years, searching for the telltale dips in brightness that indicates a planet passing in front of its star. The mission was spectacularly successful, discovering thousands of exoplanets and showing that planets are common. Most stars have at least one planet, and many have multiple planets. Transit observations provide information that radial velocity measurements cannot. The depth of the transit, how much the star's brightness decreases, reveals the planet's size. A bigger planet blocks more light, creating a deeper transit. The duration of the transit reveals information about the planet's orbital distance and the star's size. By combining transit observations with radial velocity measurements, astronomers can determine both the planet's size and its mass, which allows them to calculate its density and infer what it might be made of. A low-density planet is probably a gas giant like Jupiter. A high-density planet is likely rocky like Earth. A medium density might indicate a water world or a planet with a thick atmosphere. The transit method has limitations. It only works for planets whose orbits happen to be aligned edge-on from Earth's perspective. If a planetary system is tilted so that planets pass above or below the star rather than directly in front of it, no transits occur, and the planets remain undetectable by this method. Statistically, only a small fraction of planets are oriented correctly for transits to be visible from Earth. For a planet at Earth's distance from a Sun-like star, the probability of correct alignment is less than 1%. Despite this limitation, Kepler's strategy of monitoring thousands of stars simultaneously meant that even with low individual probabilities, many planets were discovered. Direct imaging represents the most straightforward approach, actually taking a picture of the planet next to its star, but it's also the most technically challenging. The problem is the enormous brightness difference. A Sun-like star is typically 10 billion times brighter than a Jupiter-like planet at visible wavelengths, and the planet sits right next to the star in the sky. Special techniques are required to block the star's light and reveal the faint planet. Coronagraphs, which create an artificial eclipse by placing a mask over the star, and star shades, which fly separately from the telescope and block the star's light before it enters the telescope, both enable direct imaging. Direct imaging works best for young, massive planets that are far from their stars. Young planets are still hot from their formation, glowing brightly in infrared light, making the contrast ratio more favourable. Planets farther from their stars are more separated in angle, making them easier to distinguish from the star's glare. Several dozen planets have been directly imaged, mostly young gas giants orbiting at large distances from their stars. These planets appear as faint dots of light in images taken with large, ground-based telescopes equipped with adaptive optics systems that correct for atmospheric blurring. Gravitational microlensing provides another method for detecting exoplanets, particularly useful for finding planets at large distances from Earth and planets far from their host stars. The technique relies on general relativity. When one star passes almost directly in front of a more distant background star from Earth's perspective, the foreground star's gravity acts as a lens, bending and focusing the background star's light. This creates a temporary brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence. Microlensing events are rare and unpredictable. You can't choose to observe a particular star and wait for a microlensing event. Instead, astronomers monitor millions of stars in dense stellar regions, like the galactic bulge, waiting for events to occur. When an event happens, it's unique. The same foreground and background star will never align again in human timescales. This makes follow-up observations challenging, but the method has discovered several dozen planets and is particularly good at finding planets in the outer reaches of planetary systems where other methods struggle. Astrometry measures the precise position of a star in the sky over time. If a planet is present, the star wobbles back and forth on the sky, shifting position slightly as both star and planet orbit their common center of mass. This is similar to the radial velocity method, but measures the wobble in position rather than in velocity. The wobble is extremely small. For Jupiter orbiting the Sun, as seen from a distance of 10 light-years, the wobble would be about half a millisecond, roughly equivalent to measuring the width of a human hair from a distance of 200 miles. The European Space Agency's Gaia mission, launched in 2013, is measuring the positions of over 1 billion stars with unprecedented precision, and it's beginning to detect the astrometric wobbles caused by giant planets. As Gaia continues its mission and accumulates more data, it will discover planets through astrometry and provide three-dimensional orbital information for many planets discovered by other methods. Each detection method has biases. It favors finding certain types of planets over others. Radial velocity finds massive planets close to their stars. Transits find planets of all masses, but only those aligned edge-on. Direct imaging finds young massive planets far from their stars. Microlensing finds planets at all distances but works best for planets far from their stars. By using multiple methods, astronomers build a more complete picture of the diversity of planetary systems. The combination of techniques has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury. Super-Earths, planets larger than Earth but smaller than Neptune, appear to be extremely common, yet don't exist in our solar system. Some systems have planets in extremely compact orbits, with multiple planets packed closer to their star than Mercury is to our Sun. Other systems have planets on highly eccentric orbits, stretching from close in to far out in elongated ellipses. Some planets orbit binary stars, experiencing sunsets with two suns like Luke Skywalker's home planet Tatooine in Star Wars. The atmospheres of exoplanets can be studied through transit spectroscopy. When a planet transits its star, some starlight filters through the planet's atmosphere on its way to Earth. Different molecules in the atmosphere absorb light at specific wavelengths, creating an absorption spectrum that reveals the atmospheric composition. Astronomers have detected water vapor, methane, carbon dioxide, and other molecules in exoplanet atmospheres. The James Webb Space Telescope, launched in 2021, is revolutionizing this field with its ability to detect even fainter spectral signatures and characterize the atmospheres of smaller, potentially habitable planets. The search for Earth-like planets in habitable zones, the region around a star where temperatures allow liquid water to exist on a planet's surface, drives much exoplanet research. Kepler discovered several candidates, including Kepler 452b, a planet slightly larger than Earth orbiting a Sun-like star at a distance where temperatures might support liquid water. Whether any of these planets actually harbour life remains unknown, but the discovery that Earth-sized planets in habitable zones exist at all is profound. We're no longer wondering whether such planets exist, but rather whether any of them host life. Future missions will improve our ability to find and characterize Earth-like planets. The Nancy Grace Roman Space Telescope will use microlensing and direct imaging to find planets. Ground-based extremely large telescopes currently under construction will directly image planets and study their atmospheres in detail. Proposed missions like the Habitable Worlds Observatory aim to directly image dozens of Earth-like planets and search their atmospheres for biosignatures, gases like oxygen and methane that might indicate the presence of life. In less than 3 decades, exoplanet science has progressed from the first tentative discovery to finding thousands of planets, characterizing their properties, studying their atmospheres, and identifying candidates that might harbor life. The methods astronomers developed to overcome the challenge of finding tiny, faint planets next to brilliant stars have succeeded beyond initial expectations, revealing that planets are not rare accidents but common outcomes of star formation. That our solar system is just one example among billions of planetary systems filling the galaxy, and that the question of whether we're alone in the universe might finally be answerable through observations of the atmospheres of distant worlds orbiting alien suns. How fast you'd need to go to leave a planet. Every object massive enough to have significant gravity holds onto anything near its surface. A ball thrown upward eventually falls back down. A bird must constantly flap its wings to stay aloft. Even the fastest jet aircraft cannot fly into space. Eventually it runs out of altitude and must descend. To truly leave a planet, to escape its gravitational grip entirely and coast into space without using any more fuel, you must reach a specific speed called escape velocity. This critical speed depends on the planet's mass and size, and understanding it reveals why launching rockets is so difficult, why some worlds can hold atmospheres while others cannot, and why the smallest push can send an astronaut drifting away from an asteroid while escaping Earth requires enormous rockets, burning millions of pounds of fuel. Escape velocity is not about reaching a particular altitude or getting above the atmosphere. It's about speed, specifically moving fast enough that your kinetic energy equals or exceeds the gravitational potential energy binding you to the planet. If you launch something straight up at exactly escape velocity, it will climb higher and higher, slowing down continuously as gravity pulls it back, but never quite stopping. It will coast to infinite distance, arriving there with zero velocity, having converted all its initial kinetic energy into potential energy. Launch at any speed less than escape velocity, and gravity eventually wins, pulling the object back down. For Earth, escape velocity at the surface is about 11 kilometers per second, roughly 40,000 kilometers per hour, or about 25,000 miles per hour. This is more than 30 times faster than a typical passenger jet flies. To reach this speed, starting from rest requires enormous amounts of energy, which is why rockets are so large and burn so much fuel. The Saturn V rocket that launched Apollo missions to the Moon stood over 100 meters tall and weighed more than 2,000 tons at launch. But only about 50 tons of that mass, less than 3%, was the actual Apollo spacecraft and crew. Everything else was fuel and engines needed to accelerate that relatively small payload to the speeds necessary for spaceflight. Escape velocity depends on two factors: the planet's mass and its radius. More massive planets have higher escape velocities because stronger gravity pulls harder, requiring more speed to escape. Larger planets, meaning planets with larger radii, have lower escape velocities at their surfaces because you start farther from the center of mass where gravity is weaker. Earth is more massive than Mars, but also larger, and the combination means Earth's escape velocity is about 4.5 kilometers per second, higher than Mars's escape velocity of roughly 5 kilometers per second. This makes Mars somewhat easier to launch from than Earth. A rocket leaving Mars needs to reach only about half the speed required to leave Earth, which translates to roughly 1/4 the energy. Energy requirements scaled with the square of velocity. Mars's thinner atmosphere also helps, creating less air resistance during ascent. These factors make Mars an attractive location for future space missions that might launch from the surface to explore the outer solar system or return to Earth. The Moon, much smaller and less massive than Earth, has an escape velocity of only about 2.5 kilometers per second, less than 1/4 Earth's escape velocity. This made the Apollo lunar module's ascent from the Moon's surface relatively straightforward compared to launching from Earth. The ascent stage needed far less fuel and could use a much smaller engine. The low escape velocity also meant that the lunar module could take off without the massive multi-stage rockets required for Earth launch, using a single engine to reach lunar orbit directly. Jupiter, the most massive planet in our solar system, has an escape velocity from its cloud tops of about 60 kilometers per second, more than 5 times Earth's escape velocity. Launching from Jupiter, if there were a solid surface to launch from, would require vastly more energy than launching from Earth. Any spacecraft falling into Jupiter's atmosphere would need extraordinary speeds to escape again, which is why missions to Jupiter use gravity assists from other planets to gain speed rather than attempting to enter and exit Jupiter's deep gravity well. The concept of escape velocity explains why planets can hold atmospheres, while asteroids and comets cannot. Gas molecules in an atmosphere move at speeds related to temperature. Hotter gases move faster. For an atmosphere to remain bound to a body over billions of years, the typical speed of atmospheric molecules must be significantly lower than escape velocity. If molecules regularly reach speeds close to or exceeding escape velocity through random thermal motion, they leak away into space. Earth's atmosphere consists primarily of nitrogen and oxygen molecules that move at average speeds of a few hundred meters per second at normal temperatures, well below escape velocity. The lightest element, hydrogen, moves much faster at the same temperature because lighter molecules move faster for a given thermal energy. Hydrogen molecules at Earth's atmospheric temperature move at average speeds around 2 kilometers per second, which is still well below escape velocity, but close enough that over billions of years, Earth has lost most of its primordial hydrogen. The Moon's escape velocity is low enough that essentially no gas can remain in a lunar atmosphere. Any molecules would need to be extremely cold to have velocities below escape velocity, but solar heating warms the lunar surface during the long lunar day, giving molecules enough energy to escape. This is why the Moon has no atmosphere. Its weak gravity cannot hold even the lightest gases against thermal evaporation. Mars, with escape velocity between the Moon's and Earth's, represents an intermediate case. Mars can hold heavier molecules, like carbon dioxide in its atmosphere, but it loses lighter molecules more easily. Mars also lacks a strong magnetic field to protect its atmosphere from the solar wind, the stream of charged particles from the Sun. Over billions of years, the solar wind has stripped away most of Mars's original atmosphere, leaving the thin atmosphere we observe today. Escape velocity decreases with altitude. At the surface, you need to reach Earth's full escape velocity of 11 kilometers per second. But at the altitude where the International Space Station orbits, about 400 kilometers up, escape velocity is slightly less, around 10.9 kilometers per second. The difference is small because 400 kilometers is not much compared to Earth's radius of about 6,400 kilometers. But at lunar distance, about 380,000 kilometers, escape velocity from Earth has dropped to only about 1 kilometer per second. Apollo spacecraft needed to reach only this lower speed to escape Earth's gravity after coasting most of the way to the Moon. Escape velocity is the same in all directions. You could launch straight, up, horizontally, or at any angle, and you'd need the same speed to escape. The direction doesn't matter for escape, only the speed. However, in practice, rockets don't launch straight up. They curve their trajectory to gain horizontal velocity as well as altitude, because horizontal velocity is what's needed for orbit. Reaching escape velocity while moving horizontally means you escape while also having momentum that carries you away from the planet, rather than climbing straight up until you barely escape with zero velocity. Black holes represent the extreme case of escape velocity. At the event horizon, the boundary of a black hole, escape velocity equals the speed of light. Nothing can move faster than light, so nothing can escape from within the event horizon. This is what makes a black hole black. Not even light can escape once it crosses this boundary. For a black hole with a few times the Sun's mass, the event horizon has a radius of only about 10 kilometers. The extreme compression of mass into such a small radius creates escape velocities that reach and exceed the cosmic speed limit. Interestingly, you don't have to reach escape velocity to get into space. Rockets reaching orbit around Earth need to achieve only about 8 kilometers per second at orbital altitude, less than escape velocity. Orbital velocity is the speed at which your sideways motion exactly balances gravitational pull, so you continuously fall around the planet rather than falling back to it. This is easier to achieve than escape velocity, which is why orbital missions are more common than interplanetary missions. The Space Shuttle, for example, accelerated to about 8 kilometers per second to reach low Earth orbit, then used additional fuel to accelerate to higher speeds only when needed for missions to higher orbits or to the International Space Station. Missions leaving Earth orbit for the Moon, Mars, or other destinations required additional speed beyond orbital velocity to reach escape velocity and break free of Earth's gravity. Understanding escape velocity also explains how gravity assists work. When a spacecraft flies past a planet on a carefully calculated trajectory, it can gain speed by essentially stealing a tiny amount of the planet's orbital momentum. From the spacecraft's perspective, it falls toward the planet, swings around it, and flies away. If the trajectory is chosen correctly, the spacecraft leaves moving faster relative to the Sun than it arrived, having been accelerated by the planet's gravity without burning any fuel. The Voyager spacecraft used multiple gravity assists from Jupiter and Saturn to reach speeds high enough to eventually escape the solar system entirely, crossing into interstellar space decades after launch. Calculating how fast you'd need to go to leave a planet comes down to a simple formula involving the planet's mass and radius, derived from Newton's law of universal gravitation. The energy required to escape grows with planetary mass and shrinks with planetary radius, creating the variety of escape velocities we observe throughout the solar system. From tiny asteroids where you could literally jump into space if you weren't careful, to massive Jupiter where even the most powerful rockets would struggle to escape, the speed required to leave a world tells us about that world's fundamental properties and shapes everything from how we design spacecraft to which worlds can hold atmospheres, determining the accessibility of each destination in our cosmic neighborhood and beyond. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, this zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice, material that spacecraft have flown through and analyzed. The presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favorable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbour life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harbouring biospheres in their hidden oceans. Binary star systems, where two stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from two suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets and the basic ingredients for life: elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. How evolution would work on other worlds. Evolution is not a theory specific to Earth. It is a fundamental principle that must operate wherever life exists, as inevitable as gravity or thermodynamics. The basic mechanism is elegantly simple. Organisms that are better suited to their environment tend to survive and reproduce more successfully than those less well suited, passing their advantageous traits to offspring. Over countless generations, this process of natural selection shapes organisms to fit their environments with remarkable precision. Charles Darwin recognized this principle in the 19th century by studying finches on the Galapagos Islands and countless other organisms, but the principle extends far beyond Earth. On any world where life emerges, evolution would be the engine driving biological diversity and adaptation, though the specific outcomes would be shaped by each world's unique conditions. The fundamental requirements for evolution are remarkably minimal. Life must be able to reproduce, creating offspring. There must be variation among individuals. No two organisms are exactly alike. Some of this variation must be heritable, passed from parents to offspring, and there must be differential survival and reproduction. Some variants survive and reproduce more successfully than others. These conditions create evolution automatically, inevitably, as surely as releasing a ball on a slope causes it to roll downhill. Any replicating system with heritable variation and selection will evolve, whether it's based on DNA, some other information storage molecule, or even non-biological replicating systems. On Earth, DNA serves as the information storage medium for nearly all life. The DNA molecule consists of two strands wrapped around each other in a double helix, with each strand composed of a sugar phosphate backbone and a sequence of 4 bases: adenine, thymine, guanine, and cytosine. The sequence of these bases encodes genetic information, and this information is copied when cells divide, passed to offspring when organisms reproduce. Mutations, random changes in the DNA sequence caused by copying errors, radiation, chemical damage, or other factors, create the variation upon which natural selection acts. But DNA is not the only possible genetic molecule. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information and be copied, yet use different sugars or even different backbone structures than natural DNA and RNA. These artificial genetic molecules demonstrate that information storage and heredity don't require DNA specifically. An alien organism might use a completely different molecule to store genetic information, perhaps based on different chemistry more suited to its world's conditions. A very cold world might favor genetic molecules that are stable and flexible at low temperatures. A very hot world might favor molecules that resist heat degradation. The specific molecule doesn't matter. What matters is that it can store information, be copied with reasonable but imperfect fidelity, and allow variation to arise. The timescales of evolution would differ dramatically on different worlds. On Earth, bacterial generations might span minutes to hours, allowing rapid evolution. The bacteria that cause diseases evolve antibiotic resistance within years or decades as antibiotics create selection pressure, favoring resistant strains. In contrast, large organisms with long generation times evolve more slowly. Elephants with generation times of decades evolve far more slowly than bacteria. On an alien world where organisms have extremely long lifespans, perhaps living for thousands of years, evolution would proceed at a glacial pace from a human perspective, with significant changes taking millions or billions of years. Conversely, on a world where organisms reproduce very rapidly, evolution might proceed at dizzying speeds. If alien microorganisms reproduced every few minutes, like some Earth bacteria, they could evolve through thousands of generations while we watched. Such organisms might adapt to new conditions, almost in real time, developing resistance to threats or exploiting new resources faster than slower evolving species could respond. The environment determines what traits are advantageous. On Earth, giraffes evolved long necks because reaching high branches provided access to food that shorter animals couldn't exploit. Cheetahs evolved extreme speed to catch fast prey. Cacti evolved to store water and reduce surface area in desert environments. Each adaptation reflects the specific challenges and opportunities of the organism's environment. On alien worlds, different environments would favor different adaptations. On a high-gravity planet, evolution would favor short, stocky body plans with strong skeletons and powerful muscles to support body weight against stronger gravitational pull. Tall, slender organisms would be at a disadvantage because the structural demands of supporting height would be too great. Flying organisms might be rare or absent because overcoming gravity to achieve flight would require enormous energy expenditure. Over millions of generations, organisms would become increasingly adapted to moving efficiently under high gravity, perhaps developing 4 legs or even 6 or 8 for stability, with low centers of gravity and massive muscular systems. On a low-gravity world, the opposite pressures would apply. Organisms could afford to be tall and slender because less structural support is needed. Flight might be easy, favoring the evolution of wings and aerial lifestyles. Animals might leap enormous distances because the energy required to overcome gravity would be minimal. Over time, organisms might evolve increasingly delicate structures, abandoning the heavy skeletons and dense muscles necessary on higher gravity worlds in favor of lighter, more energy-efficient body plans. Atmospheric composition would profoundly influence evolution. On Earth, the transition from an oxygen-poor to an oxygen-rich atmosphere about 2.5 billion years ago, the Great Oxidation Event, was catastrophic for organisms adapted to the old atmosphere. Oxygen was toxic to them, and they retreated to oxygen-free refuges or went extinct. But for organisms that could tolerate or use oxygen, this chemical change created opportunities. Oxygen metabolism releases far more energy than anaerobic metabolism, enabling the evolution of larger, more active, more complex organisms. The size of organisms on Earth is ultimately limited by how efficiently they can deliver oxygen to their cells. On a world that never develops an oxygen-rich atmosphere, organisms might remain permanently small and metabolically limited. Without the high energy yield of oxygen metabolism, active lifestyles like those of birds, mammals, or even fish might be impossible. Life might consist entirely of small, slowly moving organisms eking out existence on the limited energy available from anaerobic metabolism. Or evolution might discover entirely different high-energy metabolic pathways based on different oxidizing agents, perhaps sulfur compounds, chlorine, or substances we haven't considered. The availability of water determines many evolutionary paths. On Earth, life originated in water, and even terrestrial organisms remain fundamentally aquatic. Our cells are filled with water, and we constantly need to replenish water lost to evaporation and excretion. On a water-rich world with extensive oceans, evolution might produce countless aquatic species, but might never develop terrestrial life if there's no advantage to leaving water. On a dry world with limited water, evolution would favor organisms that conserve water ruthlessly, perhaps evolving impermeable skins, efficient kidneys, metabolic water production, or even the ability to extract water from food or from humidity and air. Predation creates powerful selection pressures that drive evolutionary arms races. Prey evolve defenses, armor, toxins, speed, camouflage, while predators evolve counter-adaptations to overcome those defenses. Stronger jaws, detoxification mechanisms, greater speed, better sensory systems. This coevolution produces increasingly sophisticated organisms on both sides. On Earth, the evolution of predators coincides with the evolution of many complex features: eyes to detect prey, brains to process sensory information and coordinate hunting strategies, complex behaviors for stalking and capturing prey. On alien worlds, predation would likely emerge wherever life becomes sufficiently complex, driving similar evolutionary arms races, but the specific adaptations would reflect the alien environment. On a world with dense fog or darkness, evolution might favor chemical or acoustic sensing over vision. On a world with three-dimensional environments, like open water or thick forests, predators might evolve better spatial perception and three-dimensional maneuverability. On a world where prey can burrow or fly, predators would evolve means to follow them into those refuges. Sexual selection, where organisms choose mates based on specific traits, creates another evolutionary force. On Earth, peacocks evolved elaborate tails, not because those tails help survival, but because peahens prefer males with impressive tails. This sexual selection can drive the evolution of traits that actually reduce survival, but increase reproductive success. On alien worlds, whatever traits the choosing sex prefers would be amplified through generations, potentially creating wildly extravagant features that serve no purpose beyond attracting mates. Convergent evolution, where unrelated organisms independently evolve similar solutions to similar problems, demonstrates that certain designs work well for certain challenges. Eyes evolved independently many times on Earth because detecting light provides such valuable information that natural selection repeatedly favored organisms with improved light-sensing abilities. Wings evolved independently in insects, birds, bats, and pterosaurs because flight provides such significant advantages that multiple lineages evolved aerial capabilities. On alien worlds, convergent evolution would operate similarly. Any organism that needs to move quickly through water would likely evolve a streamlined body shape because physics dictates that this shape minimizes drag. Any organism that needs to see would likely evolve some structure that focuses light onto photosensitive cells, though the specific implementation might differ. Any organism that needs to manipulate objects would likely evolve some form of grasping appendages. The specific details would vary. Alien hands might have 3 fingers or 7, might be at the end of tentacles or rigid arms, might use suction or hooks instead of friction, but the basic function of grasping would emerge wherever it provides advantage. However, historical contingency, the accidents of evolutionary history, also plays a crucial role. Vertebrates on Earth have 4 limbs because that's what the early fish that first crawled onto land happened to have. There's nothing inevitable about the number 4. If a 6-limbed fish had been the first successful land colonizer, terrestrial vertebrates might all have 6 limbs today. On alien worlds, similar historical accidents would lock in features that become constraints on all future evolution. An early successful body plan might dominate an entire planet's evolutionary tree, with all descendants constrained by that ancestral architecture. Mass extinctions reset evolutionary trajectories. On Earth, the asteroid impact 66 million years ago that killed the non-avian dinosaurs allowed mammals, previously small nocturnal creatures, to diversify into the enormous variety we see today. Without that extinction, mammals might have remained small and marginal while dinosaurs continued dominating. On alien worlds, whatever catastrophes occur, asteroid impacts, volcanic eruptions, climate changes, nearby supernova, would similarly reset evolution, wiping out dominant groups and allowing previously marginal organisms to radiate into newly available ecological roles. The speed of environmental change influences evolutionary dynamics. Rapidly changing environments favour organisms with short generation times and high mutation rates that can adapt quickly. Stable environments favour organisms optimised for efficiency in unchanging conditions. An alien world with a highly variable climate, perhaps due to an eccentric orbit or an unstable star, would see evolution favouring adaptable generalists. A world with stable conditions for billions of years might produce highly specialised organisms, exquisitely adapted to narrow niches, but unable to cope with change. Intelligence itself is an evolutionary adaptation that emerged on Earth because it provided survival and reproductive advantages. Brains require enormous energy. Human brains consume about 20% of our total energy, despite being only 2% of body mass. This high cost means intelligence only evolves when its benefits outweigh its costs. On Earth, intelligence apparently provided sufficient advantage through tool use, social cooperation, and problem solving to justify the expense. On alien worlds, whether intelligence evolves depends on whether similar advantages exist. Some environments might favour intelligence more strongly than Earth did. A highly variable environment where adaptability is crucial might select strongly for intelligence and behavioural flexibility. A world where organisms compete primarily through social manipulation rather than physical prowess might favour intelligence. Conversely, some worlds might never produce intelligence because simpler solutions always work well enough. If food is always abundant and predators are absent, the energy costs of maintaining a large brain might never be justified. How evolution would work on other worlds follows the same fundamental principles that operate on Earth: variation, heredity, and selection, but expresses those principles through the unique circumstances of each world. A high-gravity planet would sculpt short, powerful organisms. A dark world might favour chemical sensing over vision. A frigid world might produce organisms with anti-freeze biochemistry and slow metabolisms. Each world would develop its own evolutionary history, branching from simple origins into complexity through billions of years of selection, extinction, radiation, and adaptation, creating ecosystems and organisms as unique as fingerprints, yet fundamentally related through the universal principles of evolution that must operate wherever life exists, proving that while life-specific forms might be infinitely varied across the cosmos, the process that shapes life, evolution through natural selection, remains constant, an inevitable consequence of imperfect replication and limited resources operating across deep time on any world that hosts living things. The bright and dark features on surfaces. Across the solar system, the surfaces of planets, moons, and asteroids display remarkable contrasts between light and dark regions. These variations in brightness, called albedo features, paint cosmic bodies with patterns that range from subtle shadings to stark contrasts, each telling a story about composition, geology, and the forces that have shaped these worlds over billions of years. Consider Earth's moon, the most familiar example. Even without a telescope, you can see the dramatic difference between the bright highlands and the dark Maria, the ancient lava plains that early observers mistook for seas. The bright regions are ancient crust formed over 4 billion years ago when the moon was young and its surface was still cooling from a molten state. This primordial crust is rich in a mineral called anorthosite, a type of rock that's relatively light in colour and highly reflective. These highlands are the original surface of the moon, battered by eons of meteorite impacts, but still retaining their pale character. The dark Maria formed later, between about 3.8 and 3.1 billion years ago, when massive asteroid impacts punched through the moon's crust and allowed molten rock from the interior to flood onto the surface. This lava was basaltic, similar to the lava that flows from volcanoes in Hawaii, and it's much darker than the highland material. The basalt contains more iron and magnesium than the ancient crust, and these elements absorb more light, giving the Maria their characteristic dark appearance. When this lava cooled and solidified, it created vast, smooth plains that still dominate the near side of the moon today. The moon's far side presents a different face, with far fewer dark Maria and much more bright highland terrain. This asymmetry puzzled scientists for decades. Why would one side of the moon have so much volcanic flooding, while the other side remained mostly ancient highland? The answer lies in the moon's structure. The crust on the far side is thicker, making it harder for lava to break through, even when massive impacts occurred. The near side's thinner crust allowed molten rock to more easily reach the surface, creating the face we see each night. Mars displays its own dramatic albedo patterns, visible even through small telescopes from Earth. The planet shows bright regions and dark regions that early astronomers mapped and named, imagining them to be continents and seas. The bright areas are primarily ancient highland regions, covered with fine dust that's rich in iron oxide, essentially rust, giving Mars its characteristic red colour. This dust is incredibly fine, almost like talcum powder, and it reflects sunlight fairly efficiently despite its red hue. The dark regions on Mars are areas where the dust has been blown away by winds, exposing darker underlying rock or concentrations of dark sand. Some of these features change over time as seasonal winds redistribute dust across the planet's surface. During global dust storms, which can envelope the entire planet, the contrast between bright and dark features diminishes as everything gets covered in suspended dust. As the storm settles, the patterns gradually re-emerge, though sometimes in slightly different configurations than before. One of Mars's most prominent dark features is Syrtis Major, a broad shield volcano whose dark basaltic rock stands in stark contrast to the surrounding bright highlands. This feature was one of the first to be recognized on Mars and has been used for centuries to track the planet's rotation. The dark rock here is volcanic in origin, similar to the moon's Maria, and it resists being covered by the bright dust that blankets much of the planet. Mercury, the innermost planet, shows subtle but distinct albedo variations across its heavily cratered surface. The overall planet is fairly dark, reflecting only about 12% of the sunlight that hits it, making it one of the least reflective rocky bodies in the solar system. But within this generally dark surface, brighter and darker regions exist. Some craters have bright rays extending from them, where the impact that formed the crater excavated fresher material from beneath Mercury's space-weathered surface and scattered it across the surrounding landscape. The darker regions on Mercury include vast, smooth plains that, like the Moon's Maria, formed when lava flooded the surface billions of years ago. But Mercury also has mysterious dark material that appears to have been deposited from volcanic eruptions in a more explosive fashion. This dark material, which may be rich in carbon or other volatile rich compounds, creates some of the darkest features on the planet's surface, appearing almost black in high-resolution images. Jupiter's moon Europa presents one of the most striking albedo contrasts in the solar system. The moon's surface is almost entirely water ice, but it's not uniformly bright. The cleanest ice is brilliantly white, reflecting nearly all the sunlight that touches it. But cutting across this bright surface are countless dark lines and streaks, forming patterns that remind observers of cracks in pack ice on Earth. These dark features are ridges and bands where the ice has fractured and material from beneath, perhaps salts, sulfur compounds, or organic molecules, has been exposed or deposited on the surface. Some of Europa's dark features appear reddish-brown, suggesting the presence of salts like magnesium sulfate or sodium chloride that have been altered by radiation from Jupiter's intense magnetic field. The radiation breaks apart molecules and creates new compounds, darkening and discoloring the surface materials over time. The brightest regions on Europa are thought to be the youngest, places where fresh ice has recently been exposed or deposited, while the darker, more discolored regions are older surfaces that have been exposed to radiation for longer periods. Saturn's moon Iapetus displays perhaps the most dramatic albedo contrast of any body in the solar system. One hemisphere is as bright as fresh snow, reflecting about 60% of incoming sunlight, while the other hemisphere is as dark as asphalt, reflecting only about 4%. The boundary between these regions is sharp and striking, creating an appearance that reminded astronomers of a yin-yang symbol. The dark material, concentrated primarily on the leading hemisphere, the side that faces forward as Iapetus orbits Saturn, may have originated from dark dust in Saturn's system that Iapetus swept up as it moved through space, or it may have erupted from the moon's interior through cryovolcanic processes. Once the initial dark material was deposited, a feedback process likely amplified the contrast. Dark surfaces absorb more sunlight and heat up more during the day. On Iapetus, where daytime temperatures can reach as high as -230 degrees Fahrenheit in sunny areas, this slight extra heating in the dark regions causes water ice to slowly sublimate, transition directly from solid to vapor. This water vapor migrates to colder regions, including the bright trailing hemisphere, where it refreezes. Over millions of years, this process has darkened the dark hemisphere further by removing its ice and brightened the bright hemisphere by depositing additional ice there. Pluto, visited by NASA's New Horizons spacecraft in 2015, revealed a surface of surprising complexity and dramatic albedo contrasts. The dwarf planet's most prominent dark feature, informally named Cthulhu Regio, is a vast region near the equator that appears deep red-brown in colour. This dark material is thought to be complex organic molecules called tholins, formed when ultraviolet light from the distant sun and cosmic rays interact with methane and nitrogen in Pluto's thin atmosphere. These molecules rain down onto the surface, accumulating over time and creating the dark coloration. Adjacent to this dark region lies Sputnik Planitia, a vast plain of bright nitrogen ice that forms the western lobe of Pluto's heart-shaped feature. This bright ice reflects much more light than the surrounding terrain. The contrast exists because nitrogen ice is relatively bright and because this region is geologically active. The ice is constantly churning in slow convection cells, bringing fresh material to the surface and preventing the accumulation of the dark organic compounds that colour other parts of Pluto. Asteroids show their own albedo variations, though measuring them requires careful observation. Some asteroids are quite dark, reflecting only 3 or 4% of the light that hits them. These are typically carbonaceous asteroids, rich in carbon compounds and hydrated minerals, making them among the darkest natural objects known. Other asteroids are much brighter, particularly those made primarily of metal or rocky silicates. The contrast between dark and bright asteroids tells scientists about their composition and helps trace them back to different regions of the early solar system where they formed. Even within a single asteroid, albedo features can exist. Some asteroids show bright spots that might be exposed fresh material where an impact has recently broken through a darkened, space-weathered surface layer. Others show variations that might indicate different minerals or rock types at the surface. The asteroid Vesta, one of the largest in the main belt, shows dramatic brightness variations across its surface, with some regions nearly twice as reflective as others. The process called space weathering affects the brightness of surfaces throughout the solar system. When cosmic rays, solar wind particles, and micrometeorites bombard a surface over time, they gradually darken it and change its reflective properties. Fresh surfaces, recently exposed by impacts or other processes, appear brighter. Ancient surfaces that have been exposed to space for billions of years generally appear darker and redder than they would if the same material were fresh. On the Moon, this space weathering creates the subtle variations in brightness visible within both the highlands and the Maria. The rays around young craters appear bright because the impact has excavated fresh material. Over hundreds of millions of years, these rays gradually fade as space weathering darkens the ejected material, causing it to blend in with the surrounding ancient terrain. Comets show extreme albedo contrasts as well. The nucleus of a comet, the solid body beneath the gas and dust, is among the darkest objects in the solar system, often reflecting only about 4% of incident light. This dark material is thought to be a mixture of organic compounds, similar to the tholins on Pluto, mixed with dust and ice. But when a comet approaches the Sun and begins to release gas and dust, it can develop bright areas where fresh ice is exposed and actively sublimating, creating jets of gas that appear much brighter than the surrounding dark nucleus. The study of albedo features requires careful measurement. Scientists use photometry to measure exactly how much light a surface reflects at different wavelengths. By comparing the brightness at different wavelengths, they can determine not just whether a surface is bright or dark overall, but what specific materials might be present. Iron-rich minerals absorb light differently than ice, which absorbs differently than sulfur compounds or organic materials. Each substance has its own spectral signature, revealed through its albedo characteristics. These patterns of light and dark across the surfaces of solar system bodies are not mere decoration. They are maps written in brightness, showing us where different materials exist, where geologic processes have been active, where impacts have occurred, and how surfaces age under the constant bombardment of radiation and particles from space. Every bright crater ray, every dark lava plain, every reddish streak of organic material tells part of the story of how these worlds formed and evolved, creating the complex and beautiful patterns we observe across the solar system. The afterglow of the Big Bang. Throughout the entire universe, in every direction you could possibly look, there exists a faint glow of microwave radiation that fills all of space. This radiation isn't coming from stars or galaxies or any object in particular. It's coming from everywhere at once, a ghostly remnant from the earliest moments of cosmic history. This is the cosmic microwave background, the oldest light in the universe, and it carries within it a snapshot of what the cosmos looked like when it was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. To understand this afterglow, picture the universe in its earliest moments. At the very beginning, everything that exists now, all the matter and energy in hundreds of billions of galaxies, was compressed into an infinitesimally small point. The Big Bang wasn't an explosion in space, but rather an expansion of space itself. In those first fractions of a second, the universe was unimaginably hot and dense, so hot that matter as we know it couldn't exist. There were no atoms, no nuclei, not even stable protons or neutrons. There was only a seething soup of fundamental particles and energy, all in thermal equilibrium at temperatures of trillions upon trillions of degrees. As the universe expanded, it cooled, following a fundamental principle of thermodynamics. Think of how a spray can get cold when you release the compressed gas inside. Expansion causes cooling. The universe cooled rapidly in those early moments, dropping from inconceivable temperatures down to merely billions of degrees within the first few minutes. At this point, conditions became cool enough for protons and neutrons to stick together, forming the nuclei of the lightest elements, primarily hydrogen, some helium, and trace amounts of lithium and beryllium. This period, called Big Bang nucleosynthesis, lasted only about 17 minutes, but it determined the basic chemical composition of the universe for hundreds of millions of years to come. But even after nuclei formed, the universe was still far too hot for atoms to exist. Free electrons zipped through space at tremendous velocities, and any time they got near a nucleus, the ambient heat would knock them away before they could settle into orbit. The universe was filled with a plasma, a mixture of atomic nuclei and free electrons, and this plasma was opaque to light. Photons couldn't travel far before colliding with a free electron and scattering in a new direction. Light was trapped, bouncing endlessly between particles in a cosmic fog that filled all of space. For the next 380,000 years, the universe continued expanding and cooling, but it remained opaque. The temperature dropped gradually from millions of degrees down to thousands of degrees. Then at around 3,000 degrees Kelvin, still hot enough to melt any metal, something remarkable happened. The universe had finally cooled enough for electrons to combine with nuclei and form stable atoms. This moment is called recombination, though that's actually a misnomer since the electrons and nuclei were combining for the first time, not recombining. When recombination occurred, the nature of the universe changed fundamentally. With electrons now bound into atoms, there were suddenly far fewer free charged particles for photons to scatter off of. The cosmic fog cleared almost instantaneously on cosmic timescales. Light that had been trapped, scattering endlessly through the plasma, was suddenly free to travel unimpeded through space. The universe became transparent. The photons that were released at that moment of recombination have been travelling through space ever since. They filled the entire universe then, and they fill the entire universe now. These photons form the cosmic microwave background. They are the afterglow of the Big Bang, the first light that could freely travel through the cosmos. But here's the crucial part. Those photons have been stretched by the expansion of the universe. When they were released 13.8 billion years ago, they were primarily visible light and infrared radiation, corresponding to the 3,000 degree temperature of the universe at recombination. But as space itself expanded, the wavelengths of these photons were stretched along with it. Light that was once visible orange has been stretched into infrared, then into far infrared, and finally into microwave radiation. The cosmic microwave background today corresponds to a temperature of just 2.7 degrees above absolute zero, 2.7 Kelvin. This stretching of light by the expansion of space is called cosmological redshift, and it's one of the most direct pieces of evidence for the Big Bang theory. The universe has expanded by a factor of about 1,100 since recombination, and the wavelength of the cosmic microwave background radiation has been stretched by exactly this same factor. What was once a hot glow of visible light has become a cold bath of microwave radiation. The cosmic microwave background is incredibly uniform. No matter which direction you look in the sky, the temperature is almost exactly the same, 2.725 Kelvin, with variations of only about 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous. There were no large structures, no concentrations of matter, just an almost perfectly uniform distribution of hydrogen and helium gas filling all of space. But those tiny variations, those fluctuations of 1 part in 100,000, are extraordinarily important. They represent slight differences in density and temperature in the primordial plasma. Some regions were slightly denser and hotter, others slightly less dense and cooler. These fluctuations were the seeds of all structure in the universe today. The denser regions had slightly stronger gravity, which allowed them to attract more matter over time. Over hundreds of millions of years, these tiny density differences grew, eventually collapsing to form the first stars, then galaxies, then galaxy clusters, and ultimately the entire cosmic web of structure we see today. When astronomers map the cosmic microwave background in detail, they're seeing a snapshot of these primordial fluctuations. Sophisticated satellites, equipped with incredibly sensitive detectors, measure the temperature of the cosmic microwave background across the entire sky, creating maps that show warmer and cooler spots. These maps look like mottled patterns of slightly different colours, almost like abstract art, but they're actually baby pictures of the universe, showing the distribution of matter when the cosmos was just 380,000 years old. The patterns in the cosmic microwave background aren't random. They have specific statistical properties that depend on the fundamental parameters of the universe. How much normal matter exists, how much dark matter, how much dark energy, the rate of expansion, the curvature of space, and more. By analysing these patterns in exquisite detail, cosmologists can measure these parameters with remarkable precision. The cosmic microwave background has become the single most important tool for determining the basic properties of our universe. One of the most striking features visible in cosmic microwave background maps is the presence of acoustic oscillations, essentially sound waves in the primordial plasma. Before recombination, the plasma was hot and under tremendous pressure from radiation. Regions that were slightly denser had stronger gravity pulling inward, but they also had stronger radiation pressure pushing outward. These competing forces created oscillations, with dense regions compressing and then rebounding, creating waves that propagated through the plasma, much like sound waves travel through air. These acoustic oscillations were frozen into the distribution of matter at the moment of recombination. The characteristic scale of these oscillations, the typical distance between peaks and troughs, shows up as a specific pattern in the cosmic microwave background, radiation background, temperature fluctuations. By measuring this pattern precisely, astronomers can determine how far these sound waves had travelled by the time of recombination, which in turn tells them about the geometry and expansion rate of the universe. The cosmic microwave background also has a subtle property called polarization. Light can be polarized, its electric field can oscillate in a preferred direction, and the cosmic microwave background photons carry polarization information from the moment they were released. This polarization was created when the photons scattered off electrons for the last time before recombination. The pattern of polarization across the sky carries additional information about conditions in the early universe, including potentially evidence of gravitational waves from the inflationary period that may have occurred in the first tiny fraction of a second after the Big Bang. There are actually two types of polarization patterns in the cosmic microwave background, called E modes and B modes. E modes are relatively easy to detect and have been thoroughly mapped. B modes are much fainter and harder to detect, but they're particularly interesting because primordial gravitational waves would create a specific B mode pattern. Detecting this signal would provide direct evidence for cosmic inflation and would open a window into physics at energy scales far beyond what we can achieve in particle accelerators on Earth. The cosmic microwave background isn't perfectly smooth in its distribution across the sky. There's a slight asymmetry, a dipole pattern, where one side of the sky is slightly hotter and the other slightly cooler. This dipole is caused by the motion of our solar system through space. We're moving at about 370 kilometers per second relative to the cosmic microwave background, carried along by the motion of the Sun around the galaxy, the motion of the galaxy through the local group, and the motion of the local group through the universe. This motion causes the cosmic microwave background to appear slightly blue-shifted, and therefore hotter in the direction we're moving toward, and slightly red-shifted, and cooler in the direction we're moving away from. Once this dipole is removed from the data, along with contamination from our own galaxy's emission, what remains are the primordial fluctuations, the image of the universe as it was 380,000 years after the Big Bang. These fluctuations exist on multiple scales, from features spanning large portions of the sky down to the smallest angular scales that satellites can resolve. Each scale carries different information about the early universe and the physical processes that shaped it. The cosmic microwave background has also been used to test fundamental physics. The spectrum of the radiation, how much energy exists at each wavelength, matches a perfect blackbody spectrum, more precisely than any artificial source humans have ever created. This perfect blackbody spectrum is exactly what's expected from matter and radiation in perfect thermal equilibrium, providing strong confirmation that the early universe was indeed in this state. Photons from the cosmic microwave background pass through everything. Right now, billions of these ancient photons are streaming through your body every second, traveling through space for nearly 14 billion years before encountering the atoms in your cells. They pass through largely without interaction because microwave radiation interacts very weakly with ordinary matter at everyday temperatures. The entire Earth is bathed in this ancient light, as is every planet, every star, every galaxy. It's a universal background that permeates all of existence. The discovery of the cosmic microwave background in 1964 was accidental. Two radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna and kept detecting a persistent noise that came from all directions and wouldn't go away no matter what they did. They initially thought it might be interference from nearby New York City, or perhaps noise from the electronics, or even from bird droppings on the antenna. Only when they consulted with theoretical physicists did they realize they had detected the afterglow of the Big Bang, earning them the Nobel Prize. This radiation has been cooling for billions of years and will continue cooling forever. As the universe expands, the cosmic microwave background will be stretched to longer and longer wavelengths, eventually becoming radio waves, then longer wavelengths still. Its temperature will approach closer and closer to absolute zero, but will never quite reach it, always remaining as a faint reminder of the hot, dense state from which our universe emerged, carrying information about cosmic dawn across the vastness of space and time. How planets get their beautiful rings. When you think of planetary rings, Saturn immediately comes to mind, with its magnificent system of bright bands encircling the planet like a cosmic halo. But Saturn isn't alone in possessing rings. Jupiter, Uranus, and Neptune all have ring systems of their own. Though far less prominent, even some asteroids have been discovered with tiny rings circling them. These structures, some broad and bright, others narrow and faint, all share a common origin story rooted in gravity, orbital mechanics, and the sometimes violent history of the solar system. The basic ingredients for planetary rings are surprisingly simple. Countless small particles, ranging from dust grains smaller than smoke particles to chunks of rock and ice the size of houses, all orbiting a planet in a flat disk. What makes rings special isn't the individual particles but their collective behaviour, the way millions or billions of objects interact through gravity and collisions to create structures that can span hundreds of thousands of miles yet be only tens of meters thick. Rings form through several different mechanisms, and understanding these processes means understanding both creation and destruction, both gentle accumulation and catastrophic violence. The first and perhaps most dramatic way rings can form is through tidal disruption. Every planet generates a gravitational field that weakens with distance, and this creates tidal forces on any object orbiting nearby. If you imagine a moon orbiting close to a planet, the side of the moon facing the planet experiences stronger gravity than the side facing away. This difference in gravitational pull creates a stretching force that tries to pull the moon apart. There's a critical distance from any planet, called the Roche limit, inside which these tidal forces become stronger than the moon's own gravity holding it together. Cross this threshold, and the moon cannot remain intact. If a moon migrates inward through various processes, or if it formed inside this limit, it will be torn apart by tidal forces. The material doesn't disappear, it spreads out along the moon's orbital path, and over time, through collisions and gravitational interactions, it forms a flat ring around the planet. Picture this process in your mind. A small moon, perhaps captured from elsewhere in the solar system or formed in orbit around the planet, slowly spirals inward. Tidal interactions with the planet transfer energy and angular momentum, gradually changing the moon's orbit. As it crosses the Roche limit, cracks begin to form. Pieces break away, first small fragments, then larger chunks. The moon doesn't explode dramatically, it comes apart more gradually, like pulling apart a piece of bread. Each fragment continues orbiting the planet independently, and as they collide and break into smaller pieces, they spread into a disk of debris. This process may have created some of Saturn's rings, though the origin of Saturn's ring system remains one of the great puzzles in planetary science. The rings are remarkably bright and rich in water ice, suggesting they might be relatively young, perhaps only a few 100 million years old, rather than as ancient as the solar system itself. One theory suggests that a small icy moon, perhaps 200 miles across, wandered too close to Saturn and was torn apart by tidal forces. The shattered remains spread into the magnificent ring system we see today. Another way rings form is through collisions. Imagine two moons orbiting a planet on paths that eventually intersect, or an asteroid from elsewhere in the solar system crashing into a moon. The impact releases tremendous energy, shattering both objects and ejecting debris into space. Some of this material falls back onto the planet or escapes entirely, but much of it remains in orbit, gradually spreading into a ring. This collision scenario might explain some of the fainter, darker ring systems. Jupiter's rings, for instance, are composed of very small dust particles that appear reddish-brown, suggesting they might come from meteorite impacts onto small inner moons. When a meteorite strikes one of these tiny moons, it kicks up dust that then orbits Jupiter. This dust doesn't stay in the ring system forever. It gradually spirals inward due to interactions with Jupiter's magnetic field and atmospheric drag, but it's constantly replenished by new impacts. Rings can also form from a volcanic activity on moons, though this is a less common mechanism. Jupiter's moon, Io, is the most volcanically active body in the solar system, with eruptions constantly spewing material into space. Some of this material, particularly atoms of sodium and sulfur, forms extended clouds around Jupiter. While not a traditional ring of solid particles, these atomic clouds occupy ring-like regions and show that rings can have diverse origins and compositions. The shepherd moon mechanism plays a crucial role in maintaining and shaping rings once they form. Small moons orbiting just inside or outside a ring can gravitationally interact with ring particles, confining them to narrow bands. Imagine a ring particle in an orbit that would normally cause it to drift outward. As it approaches a shepherd moon, orbiting outside the ring, the moon's gravity tugs on it, altering its orbit and deflecting it back toward the ring. Similarly, a shepherd moon orbiting inside the ring can prevent particles from drifting inward. These gravitational interactions can create remarkably sharp ring edges and can even maintain gaps within ring systems. Saturn's moon Prometheus and Pandora act as shepherd moons for the narrow F ring, one of Saturn's outermost rings. The F ring is only a few hundred miles wide, but thousands of miles long, and without these shepherd moons, it would spread out and dissipate over time. The moon's gravity creates a delicate balance, continuously sculpting the ring into its narrow form. Resonances add another layer of complexity to ring formation and structure. When ring particles orbit at certain specific distances from a planet, their orbital period can be a simple fraction of a moon's orbital period, perhaps half as long, or a third or 2/5. At these resonant locations, the gravitational tugs from the moon occur at the same point in each orbit, adding up over time and creating powerful effects. Resonances can clear gaps in rings, sweeping particles out of certain orbital paths, or they can concentrate particles, creating narrow ringlets. The Cassini division, the prominent gap in Saturn's rings, visible even through small telescopes from Earth, exists primarily because of a resonance with the moon Mimas. Particles orbiting in the Cassini division have an orbital period exactly half that of Mimas. The repeated gravitational interactions at this resonance gradually push particles into different orbits, maintaining a gap nearly 3,000 miles wide. The particles within rings are not static, they're constantly colliding with each other, and these collisions shape the ring's structure and evolution. When two chunks of ice collide gently in Saturn's rings, they might stick together, growing larger. But more energetic collisions shatter particles into smaller pieces. There's a balance between these processes, and over time, rings develop a characteristic size distribution of particles, with many small particles and fewer large ones. These collisions also dissipate energy, causing the ring to flatten. Imagine particles orbiting at slightly different inclinations, some tilted a bit relative to others. When they collide, the vertical component of their motion is randomized and gradually damped out through repeated collisions. The result is that rings become extraordinarily thin relative to their width. Saturn's main rings span about 175,000 miles from inner edge to outer edge, yet they're typically only about 30 feet thick, a ratio that's thinner than a sheet of paper if scaled down. Temperature plays a role in ring dynamics as well. Ring particles are heated by sunlight and cooled by radiating infrared energy into space. The equilibrium temperature depends on the particle's size and composition. Larger particles have more thermal inertia and cool more slowly, while smaller particles respond quickly to changes in sunlight. These temperature variations affect how particles stick together when they collide, influencing whether the ring evolves toward larger clumps or maintains a population of smaller particles. The composition of ring particles varies widely between different planets and even within a single ring system. Saturn's rings are predominantly water ice, giving them their high reflectivity and bright appearance. The ice is remarkably pure, though there are trace amounts of rocky material and organic compounds that give some regions a slightly reddish or brownish tint. Uranus's rings, by contrast, are much darker, composed of material that reflects only a few % of the light that hits it. This dark material might be radiation-processed organic compounds, similar to the dark material found on some asteroids and comets. The age of ring systems is a matter of ongoing research and debate. Some rings might be primordial, dating back to the formation of the solar system itself 4.6 billion years ago. These would be rings made from material that was present in the disk of gas and dust from which the planets formed. Material that never coalesced into moons because it was inside the Roche limit. Other rings are clearly much younger, formed by relatively recent collisions or tidal disruptions. Saturn's rings, despite their prominence, might be surprisingly young. Several lines of evidence suggest they could be only a few 100 million years old. They're very bright and icy, lacking the darkening that would come from billions of years of meteorite bombardment. The amount of dust falling into Saturn's atmosphere from the rings suggests they're being depleted at a rate that couldn't be sustained over billions of years. If Saturn's rings are indeed young, it means we're living at a special time in the solar system's history, able to witness these magnificent structures during a brief window of their existence. Rings are not permanent features. They evolve over time, gradually spreading outward or inward, losing material to the planet's atmosphere or to moons, being disrupted by resonances or replenished by new collisions. Some ring systems might last for the lifetime of the solar system, while others might come and go over much shorter timescales. The rings we see today are snapshots in an ongoing process of creation, evolution, and eventual destruction. Even Earth might have had rings at some point in its distant past. Some researchers have suggested that a large impact that created debris in orbit could have temporarily given Earth a ring system that persisted for millions of years before the material either fell back to Earth or coalesced to form the Moon. While speculative, this idea reminds us that ring systems are dynamic features that can appear and disappear throughout a planet's history. The physics governing ring formation operates not just in our solar system, but around planets orbiting other stars as well. Exoplanets with large moon systems or recent collisions might sport ring systems, though detecting such rings at interstellar distances remains incredibly challenging with current technology. The same fundamental processes, tidal disruption, collisions, gravitational interactions, would operate universally, creating rings around any planet where conditions permit, adding layers of complexity and beauty to planetary systems throughout the galaxy. How the Moon pulls on Earth's oceans. Twice each day, the ocean rises up beaches and coastlines around the world, then retreats back toward the sea. This rhythmic rise and fall of the tides has shaped human civilization for thousands of years, governing when ships could enter harbours, when fishermen could gather shellfish from tidal pools, and when coastal communities needed to prepare for high water. The connection between these tides and the Moon was recognised in ancient times, but understanding exactly how the Moon creates tides requires thinking carefully about gravity, how it varies with distance, and how Earth's ocean responds to forces that stretch and squeeze it in complex ways. The fundamental cause of tides is gravity, but not gravity in the simple sense of the Moon pulling water toward itself. If that were the entire story, we would see one bulge of water on the side of Earth facing the Moon, and that would be the end of it. Instead, we observe two tidal bulges, one on the side facing the Moon and another on the opposite side of Earth. This puzzling fact confused natural philosophers for centuries, until Isaac Newton, in his Principia Mathematica, published in 1687, provided the correct explanation using his law of universal gravitation and his laws of motion. The key insight is that the Moon's gravity pulls on every part of Earth, but it pulls with different strengths depending on distance. The side of Earth closest to the Moon experiences stronger gravitational attraction than Earth's centre, which in turn experiences stronger attraction than the far side. This difference in gravitational force across Earth's diameter creates what are called tidal forces, forces that try to stretch Earth along the line, connecting it to the Moon, while simultaneously squeezing it perpendicular to that line. Imagine Earth's structure for a moment. The solid rock of Earth's crust and mantle resists deformation quite strongly. While tidal forces do deform the solid Earth slightly, raising and lowering the ground by about a foot, the effect is not dramatic because rock is stiff and strong. The oceans, however, are fluid. They can flow freely in response to forces, and they respond readily to the tidal forces that the solid Earth largely resists. Consider a point on Earth's surface directly beneath the Moon. The water at this location is about 4,000 miles closer to the Moon than Earth's center. The Moon's gravitational pull weakens with distance according to an inverse square law. Double the distance and the force becomes 1/4 as strong. This means the ocean on the near side experiences a gravitational pull toward the Moon that's about 7% stronger than the pull experienced by Earth's center. This differential force pulls the ocean away from Earth's center, creating a bulge of water on the Moon-facing side. Now consider the opposite side of Earth, the point farthest from the Moon. Here the ocean is about 4,000 miles farther from the Moon than Earth's center. The gravitational pull from the Moon at this location is about 7% weaker than at Earth's center. Earth's center is being pulled toward the Moon more strongly than the water on the far side, effectively pulling Earth away from the water and leaving the water behind. The result is another bulge on the side opposite the Moon. This creates the characteristic two-bulge pattern. If you could freeze time and look at Earth from space, you would see the oceans slightly elongated along the Earth-Moon line, with high water on both the near and far sides and low water at the points 90 degrees away from the Moon. As Earth rotates beneath these bulges, any given point on Earth's surface passes through 2 high tides and 2 low tides each day, though not exactly every 12 hours, because the Moon is also moving in its orbit, shifting the position of the bulges over time. The height of these tidal bulges would be quite modest if they responded only to the Moon's gravitational pull, perhaps a foot or 2 in the open ocean. But the actual tides we observe at coastlines can be dozens of feet high. This amplification occurs because of the way ocean basins are shaped and because of resonance effects as water sloshes back and forth in confined spaces. The Bay of Fundy in Canada experiences the world's highest tides, sometimes exceeding 50 feet, because the bay's shape and size create a natural resonance that amplifies the tidal forcing from the Moon and Sun. The Sun also creates tides on Earth, though they're smaller than lunar tides despite the Sun's vastly greater mass. The reason is distance. The Sun is about 400 times farther from Earth than the Moon, and tidal forces depend not just on mass but on how much the gravitational pull varies across Earth's diameter. The Sun's great distance means its gravitational pull varies less across Earth than the Moon's does, making solar tides about 46% as strong as lunar tides, a ratio that Pierre-Simon Laplace calculated in detail in his comprehensive work on celestial mechanics in the late 1700s. The interaction between solar and lunar tides creates the familiar spring and neap tide cycle. When the Moon and Sun align, either on the same side of Earth during a new moon or on opposite sides during a full moon, their tidal effects add together, creating spring tides with especially high high tides and especially low low tides. The name has nothing to do with the season, but comes from the idea that the tides spring forth. When the Moon and Sun are at right angles as seen from Earth during first and third quarter moons, their tidal effects partially cancel, creating neap tides with smaller tidal ranges. This 2-week cycle of spring and neap tides is predictable and was well understood by ancient mariners, though they lacked Newton's gravitational explanation for why it occurred. The timing of tides is not as simple as one might expect. If you observe the tides at any coastal location, you'll notice that high tide doesn't occur exactly when the moon is overhead, or exactly when it's on the opposite side of Earth. There's typically a delay of several hours called the tidal lag. This occurs because the ocean cannot respond instantaneously to the changing tidal forces. Water has inertia, it takes time to accelerate and decelerate, and friction between the moving water and the ocean floor dissipates energy, creating phase lags between the tidal forces and the ocean's response. These friction effects have profound long-term consequences. As tidal bulges try to follow the moon, but are dragged forward slightly by Earth's rotation, they create a gravitational pull on the moon that's not perfectly aligned with the Earth-Moon line. This misaligned pull acts to accelerate the moon in its orbit, gradually increasing its orbital energy and causing it to move away from Earth. Precise laser ranging measurements using reflectors left on the moon by Apollo astronauts have confirmed that the moon is receding from Earth at about 1.5 inches per year. This recession cannot continue indefinitely at the current rate. As the moon moves farther away, tidal effects weaken, slowing the recession. But over the 4.5 billion years since the moon formed, likely from debris created when a Mars-sized object collided with the young Earth, the moon has moved substantially farther from Earth. Early in Earth's history, when the moon was much closer, perhaps only 15,000 miles away compared to today's 240,000 miles, tidal forces were enormously stronger. Tides might have been hundreds of feet high, and the moon would have appeared many times larger in the sky, looming over the horizon like an enormous sphere dominating the heavens. The energy dissipated by tidal friction doesn't just affect the moon's orbit, it also affects Earth's rotation. The gravitational drag from the tidal bulges acts to slow Earth's rotation gradually. Each century, Earth's day lengthens by about 1.7 milliseconds. This seems negligible, but over geological time, it accumulates. Fossil evidence from ancient corals, which show daily growth bands much like tree rings, indicates that 400 million years ago, Earth's day was only about 22 hours long, and a year contained about 400 days. The moon was closer, Earth rotated faster, and tides were stronger. This tidal interaction between Earth and the moon is an example of tidal locking in progress. The moon is already tidally locked to Earth, always showing the same face toward Earth because tidal forces from Earth have synchronized the moon's rotation period with its orbital period. Earth is gradually becoming tidally locked to the moon as well, though this process will take tens of billions of years to complete, longer than the remaining lifetime of the Sun. If it could be completed eventually, Earth would always show the same face to the moon, and the moon would hang stationary in the sky over one hemisphere, never visible from the other. Other bodies in the solar system experience even more extreme tidal effects. Jupiter's moon, Io, the most volcanically active body in the solar system, is heated internally by tidal flexing. As Io orbits Jupiter in an elliptical path, the tidal forces it experiences vary in strength, squeezing and stretching the moon's interior. This constant kneading generates tremendous heat through friction, keeping Io's interior molten and driving its spectacular volcanic eruptions. This process, predicted by Stanton Peele and colleagues just before the Voyager spacecraft discovered Io's volcanism in 1979, is called tidal heating. Saturn's moon Enceladus experiences similar tidal heating, though less extreme than Io. The heat from tidal flexing keeps a subsurface ocean liquid beneath Enceladus's icy crust, and tidal stresses crack the ice at the South Pole, allowing geysers of water to erupt into space. Europa, another moon of Jupiter, likely has its subsurface ocean maintained by tidal heating as well, making it one of the most promising places to search for life beyond Earth. Tidal forces can also be destructive. Every large body creates a tidal limit, called the Roche limit, after Edouard Roche, who calculated it in 1848, inside which tidal forces exceed the self-gravity holding a satellite together. A moon that wanders inside the Roche limit will be torn apart by tidal forces, pulled into fragments that spread into a ring around the planet. Saturn's magnificent ring system may have originated this way, from a moon that either formed inside the Roche limit or migrated inward and was disrupted. Tidal forces operate throughout the universe. Binary stars experience tides that can transfer mass from one star to its companion. Black holes create tidal forces so extreme that they can tear apart stars that pass too close, creating spectacular tidal disruption events. Galaxies passing near each other experience tidal forces that stretch them into long streams of stars, creating the tidal tails visible in many interacting galaxies. The same physics that causes ocean tides on Earth, the differential pull of gravity across an extended object, operates on scales from moons and planets to stars and galaxies. The tides we observe at the beach are the local manifestation of a cosmic dance between Earth and Moon, a gravitational interaction that has been occurring since the Moon formed and will continue for billions of years into the future. Every incoming wave, every tide pool exposed at low tide, every ship waiting for high water to enter harbour is part of this larger story of how gravity shapes the motion of celestial bodies and how the Moon, our constant companion in the night sky, continues to sculpt the behaviour of Earth's oceans through the subtle but inexorable pull of tidal forces.